Alrighty, y'all, today I'm looking at question 1 for recitation number 10, when we're trying to find the speed of a particle as it's changing its electric potential energy. So for this, we're going to use our law of conservation of energy, which I kind of just alluded to, when it's going to be our initial potential energy plus our initial kinetic energy. That's going to be equal to our final potential energy and our final kinetic energy. So that's going to give us our equation for our initial potential. It's going to be Ke Q1 Q2 over R1, and this is our initial, plus 1/2 mv initial squared. It's going to be equal to our Ke Q1 Q2 over our final, plus our 1/2 mv final squared. And of course, this final velocity is what we're looking for. So I'm just going to plug in what we know. So we have our Ke times our first charge, which is 5 times 10 to the negative 6 coulombs, because those microcoulombs are just the negative 6, times our 3 microcoulombs, times 10 to the negative 6 regular coulombs. And that's our first radius, which is this 4 centimeters, because that's where it starts, and it's starting from rest. So in meters, that's going to be our 0.04 meters. And like I just said, we're starting from rest, so this initial velocity is going to be 0, making that whole term disappear. So now that's going to be equal to our final potential energy at the second point. So it's Ke Q1 Q2 over this final radius. I just didn't feel like plugging in the charges again. The final radius, though, is, again, it's in centimeters. So we're just going to convert that into meters real quick. 0.08 meters plus this 1/2, the mass of what the particle is moving, Q2 with a mass of 6 milligrams, which is going to be 6 times 10 to the negative 6 kilograms, because again, we want to keep this in the consistent units, and that's going to be times this V final squared, which is again what we're solving for. So you can do, just real quick, subtract it to the other side. I'm going to subtract this term over to here, but I'm also going to factor out the top, because this top is the same, because the charge doesn't change. So it's going to be charge Ke times 5 times 10 to the negative 6 times 3 times 10 to the negative 6. That's all going to be times, and again, it's just going to be this denominator, 1 over 0.04 minus what we subtracted across, which is the 0.08. And that's going to be equal to our 1/2 6 times 10 to the negative 6 V final squared. Now this should kind of look familiar over here, because this is essentially what you get if you do out the integral long form for your, it's the change in potential is the negative integral of Q electric field dotted with dr, right? If you do that out longhand and you're integrating from R1 to R2, that's what you're going to end up with. But instead, I didn't do that, and I took the shortcut way. So now I'm just going to divide through by these two terms here to isolate this V final. So again, it's the Ke 5 times 10 to the negative 6, 3 times 10 to the negative 6, 1 over 0.04 minus 1 over 0.08, all divided by, well, all multiplied by 1, well, divided by 1/2 is all multiplied by 2, divided by 6 times 10 to the negative 6. That's going to give us our V final squared. So we're going to take the square root, all of that, and that's what's going to give us that V final. And just from here, you're going to want to just punch it all into your calculator like you would, using our Ke equals 8.99 times 10 to the 9th, and that's going to get you a final answer for your final velocity. And since we kept all the units consistent throughout, that's going to give you your answer be final in meters per second. All right, and I hope you found all of this pretty helpful. I know it's a new format. I just got an iPad because I don't have enough credit card debt apparently. But let me know if you have any more questions about anything, or if you have any other questions that you wanted me to try to explain, because I guess Sydney explains stuff.